monitoring program, technology program at Roche, and in that capacity, he has been intensively involved in developing and applying digital markers in various disorders, and especially also in HD. And I hope that the presentation is good. So I see also people standing at the back, so there are some empty places here, so feel free to fill them up. Mm-hmm. Yeah, so I see the presentation. So please.
Thank you very much for this introduction. I will use the less complex technology here to make sure that you will all be able to hear me well. I'd like to really thank both of you, the organizers, for giving me the opportunity to speak and to present some of our latest research, the work that we've done on the Roche HD digital monitoring platform. Before I start, I would like to acknowledge everybody who has contributed to the development of the Roche digital monitoring platform. Our goal with this is to find ways how to better quantify the symptoms of multiple sclerosis so that we can more sensitively assess the effects and benefits of novel treatments on the patients and their daily lives. And to this end, patients in our trials receive a mobile phone and a smartwatch that is used then to capture, on the one hand, passive monitoring data, and on the other hand, allows study participants to contribute data via active tasks. These include questionnaires, tests of motor function, as well as of cognition. Today, I'm going to show you data from 3 tests: the speed tapping, draw shape, and chorea tests. These are done every other day during the studies. The Roche digital monitoring platform has been deployed over the last 5 years across the tominersen program, across all the studies, except for the one that Charlotte Raven took part in. That was not intentional. And in addition, it is also being used currently in an observational study, Digital HD, that includes non-carrier individuals, as well as those with pre-manifest and manifest Huntington's disease. This study is led by Professor Ed Wild, Charlotte's HD specialist. So together from all these studies, we have been able to collect data on more than 1,000 individuals with Huntington's disease. Together, they have contributed about almost 500,000 days worth of active tests and nearly 300 person-years worth of passive monitoring data. To do this, study participants have spent on average 30 to 60 minutes every single week, some of them for more than 2 years. And I cannot stress enough how grateful I am for their contribution to bring together this amazing data set. Also, of course, this is a really big data set, so that does not analyze itself overnight. We are working very hard on, and continue to work very hard on analyzing these data, but I'm very happy that I have the opportunity today to share some of the lessons we've already learned along the way. The first lesson that was not such a happy one, and that was that in Generation HD1, differential dropouts meant that we were not able to compare digital biomarker data between placebo and tominersen treatment arms. So when you deploy a digital biomarker, especially when you deploy it as an exploratory endpoint in your study, you would expect that you see some decrease in adherence over time, which here we are plotting as the fraction of study participants who have contributed at least 1 active test per fortnight. The picture stays the same when we look specifically at speed tapping. Now, we do know from our analysis that we would like to average over at least 3 repetitions of the speed tapping test out of the 7 that would be possible over 2 weeks in order to get a stable signal, and that means that we get a bit of a reduction in our data. But that is not enough. These 3 repetitions also need to be performed exactly according to protocol. However, I'm not at all surprised that within Generation HD1, the study participants contributed a very, very high quality of data, even though there was no doctor or nurse present to supervise. So thank you very much. Now, when you look at these curves, overall, they are very similar. We see that at 69 weeks, we are still just above 50% of data. That is not fantastic, but as I said, not unusual for an exploratory endpoint. And it will not be a problem for comparing treatment arms to placebo, as long as there is no difference in the study participants who do and do not collect digital data. So, of course, we checked, and what we did was to look at the clinical assessments that these patients, study participants performed, and we find that the study participants who did collect digital data, that's the ones in green, have their disease progress more slowly than the ones that in blue here that do not or have stopped collecting digital data sometime along the way. The difference that we see here, this difference is not trivial. The difference that we see at 21 weeks is about half of the total progression of the study participants who collect digital data at week 69. So that means that our placebo data is biased. It will show less, so the digital data would show less disease progression than it should, and that means we cannot use this placebo data to compare to treatment arms. In order to make sure that this will not happen anymore, we of course started to look a bit more detailed at adherence, and what we see there is that, so what we did is we did survival analysis, so to look at what is predictive of study participants dropping out of collecting digital data, and we find that the strongest predictor is the disease severity at baseline. So the worse you see HDRS, the more likely you are to stop collecting digital data sometime along the way. And this result, together with feedback that we've received from sites and from patients, suggests to us that a key culprit here is burden. Doing all the assessments all the time was too much for some of the study participants. And so we are now working on finding out, looking at ways how we can reduce that burden and hence enable the study participants to continue collect data from end to end throughout the entire clinical trial. So while we cannot use the digital data to learn about the efficacy of tominersen, we can still use it to learn about the Huntington's digital monitoring platform itself. And that brings me to the second lesson, and that is, in brief, that there are no shortcuts to developing digital biomarkers. When you take cross-sectional data, you can use that to predict what is likely going to work well in Huntington's disease. However, you do need longitudinal data to be sure. Some of you may have seen a paper that has recently come out where we used cross-sectional data to evaluate our assessments and to identify the most promising features, a feature being the number that summarizes the performance on a specific digital test. And this feature for the Korea test was the sway path. And from our cross-sectional data, we see that we have very high test-retest reliability, good correlation with cUHDRS, and also an ability to distinguish between groups. When we now looked at longitudinal data, we saw that, well, actually, it does also track disease progression very well. So that was a good prediction. However, it did not always work out that way. For the variability of the spiral drawing speed in the draw a shape test, that had actually even better ability to distinguish between groups. It could even distinguish between non-carriers and individuals with pre-manifest HD. There we find that this particular feature is not very good at tracking Huntington's longitudinally. So, as I said, you need to have this longitudinal data in order to be able to properly evaluate the digital biomarkers. Fortunately, we have these data available to us. And so we use this to now revisit all our assessments and start looking at whether these would be, how well they would be able to track disease progression in Huntington's over time. And the lesson 3 we learned there is that, yes, the Roche HD digital monitoring platform can be used to sensitively track disease progression. And what is very nice is that it even works in participants who are early in their disease course. How did we do that? So we pooled the data from 2 studies, the open label extension and the HD natural history study. And for each individual assessment, we ranked the features by looking at which ones are stable in the short term, had good correlation with the clinical anchor, changed and showed change over time. And then we used the baseline data from digital HD to make sure that if this change was, for example, going up, that the non-carrier individuals had the lowest values and the individuals with stage 2 HD had the highest value, so that the change was in the right direction. As a second step, we then took data from a slice of generation HD1 and to check or confirm that the top features that we had selected for each test remained the top feature even in an entirely different study. If that had not been the case, we would have gone back to try and find better features. As it turns out, we did not need to iterate and could go straight on to evaluating the features. And here I'm showing you the example of the speeded tapping test. To remind you, for the speeded tapping test, study participants are asked to tap on a circle on the mobile phone screen with their index finger for 30 seconds for as fast as they can. And the top feature here for the moment is the variability of the time that actually the finger spends on the screen. You can see that we see some nice change over time, that there is really good separation between different groups. This feature correlates nicely with UHDRS, very stable, and it even has an almost normal distribution at baseline, which is something that makes the statisticians really happy. However, that is of course not all we want to see. We would really like to know how well can this how sensitive is this feature really to disease progression. And for this, we're looking at what we call the signal to noise ratio. So that's the ratio between for at each time point a change from baseline as compared to the variability in this change. Higher signal to noise ratio means that you may be able to detect more subtle change, or for a given level of change, that you may be able to detect this change either earlier or with fewer patients in your study. Here we evaluate this for data from GenHD1 on study participants with HD-ISS stage 3 and compare the UHDRS finger tapping item in dark blue, CUHDRS in light blue, and the speeded tap, hour feature in red. And we see that we're consistently outperform the finger tapping item from CUHDRS by a factor of at least 2. And that in the, but what's really interesting here is that in around the 30-week mark, we're also already have really strong signal compared to CUHDRS. So that's really cool, but it gets even better. In Generation HD1, we have about 15% of the study participant with HD-ISS stage 2, and because this was a really big study, that meant we have more than data now on more than 100 study participants in this group. And when you evaluate the digital feature on that group, we see that now we're also, with our digital feature, outperforming CUHDRS consistently. And that's very impressive. From data from one finger, right, we can see better track disease progression over time in this early group in Huntington's disease. And of course, we have more than one single test, and I'm really curious to see, and we haven't done that yet, but I'm really curious to see what we're going to get when we start combining evidence from multiple tests. With this, I'd like to summarize. In Generation HD1, we have seen that there was a difference in terms of who continued and who stopped collecting digital data. This introduced a bias so that we cannot compare placebo to treatment arms to make claims about the efficacy of tominersen using this digital data. I've also shown it that over the 5 years of collecting digital data in HD, we have collected data on more than 1,000 study participants, and of which we have more than 100 with ISS stage 2 that can tell us, for example, how well the Roche HD digital monitoring platform can track disease progression. And it does seem that this is indeed possible even in individuals who are still early in their disease course. And that means the question is no longer, can we find measures in early, in HD-ISS stage 2 that can sensitively track disease progression? I think the question now is becoming how good, how much can we push this, how good do we get? Thank you.
So thank you very much, Jonas, not only for your talk, but also for keeping the time to the second.